you. Good morning, Chairman, ladies and gentlemen. It's my great honor to have a oral presentation here, and I come from HIT, and the topic I share with you is the defect detection technology for optic transparent magnetic merge thin films. So let me first introduce us. Harbin Institute of Technology is located at the northeast of China, and he is known as one of the best university for engineering in the world. And I'm a member of team lead by academic and Tan Jiubin, and more exactly, I'm in the research group of optic transparent EMI shading, and this man is my supervisor, and today I will talk in his place. So our presentation includes three parts. First is the background. As known to all, with the rapid development of wireless and electronic technology, radio frequency and microwave applications appears an explosive growth, like air pollution, water pollution, and noise pollution. The electromagnetic pollution was called the fourth major pollution. So the magnetic shielding, also known as the EML shielding, the EMI shielding is necessary in many applications. So there are many optic windows and screens in our daily life, such as the car window, the touch screen, and the observation window in the airplane. But however, regular EMI shielding materials such as metal shields and absorbing materials, they are not optical transparent. So how to achieve transparent EML shielding? Some transparent conductors are used, such as indium tin oxide, the metallic merge, nano silver, and carbon tube. So among them, the metallic merge is an important component with the listed advantage. You can see this picture. It always consists of the metal grade on the first layer, and on the second layer it's a transparent substrate. The main elevation index of the metallic merge is the shading efficiency and transparency in optical band, and also the image quality, which is related to its diffraction pattern. So there are some fundamental indices about the EML shading, such as the shading efficiency, the reflection loss options, and there is also an important figure, sheet resistance. You can see his definition here. So to get better shading efficiency and better image quality, our group have proposed different structure of metallic merge in recent years. You can see it in these figures. So it's always two ways to make a metallic merge. First is the lithography, and another is the nano imprint. So both these two production may lead to defects on the merge. So there are two typical defects of metallic merge. The first, we call it structural damage. So it's easy for visual detection, but another is high sheet resistance, and it's hard for visual detection. And the possible cause of such two defects are listed at bottom. A simulation shows both two defects have a negative impact on his shading efficiency, so it's necessary to detect them. So here we introduce a defect detection method based on microwave resonator. So first it comes the microwave non-destructive testing have some unique advantage, such as remote management. And in recent years, the research support has shifted from the antenna and waveguide to resonator with lower profile and higher sensitivity. So the main principle of the resonator-based sensor is that the resonate peak or notch will be shifted if a defect exists. You can see this picture. The resonate notch will be downshift if there are a crack. So this performance make it possible to detect such as metal surface crack and displacement. Valuation index of such sensor is sensitivity, which means the relative resonant frequency shift, and another is resolution, which is related to the Q factor of the resonance. So there are also three development trends of such sensor, and you can see them at bottom. So according to cavity perturbation theory, in a general Maxwell equation, high sheet resistance will cause lower Q factor, and cracks will cause lower resonant frequency. To design a resonator, we must notice that the energy more vertical bond, the more sensitive the sensor will be, and a smaller field lateral area always lead to better precision solution, which is similar to the concept in microscope. So this is the calculated electric and magnetic field intensity, which is different standoff distance. The standoff distance means the distance between the sensor and the material to be tested. So you can see the energy shows a rapid decline when the sensor is away from the material. So if you want to obtain a better sensitivity or better solution, you must keep the standoff distance small. To get the entropy detection, 5 Archimedes spiral slot line was used to build the complementary spiral resonator. You can also call them CSR. So it acts as a band-pass filter. It has a resonator frequency about 7.2 gigahertz, and if there are any crack, the resonant frequency will be downshift. You can see this red line, and if there are something like high sheet resistance, and there will be lower Q factor and higher insert loss, you can see in the blue line. So there are always many different structural parameters for different needs for such mechanic mesh, such as different period, line-wise, and thickness. But it is proved that different structural parameters don't affect the detection result. So similarly, there are always different cell shapes of the mechanic mesh. You can see this figure. It's a random mesh, but not like this. It's a mesh with period. So, but it also doesn't affect the detection, which means you need only one sensor and you can detect all kinds of mechanic mesh. So this is our experimental setup, and this is the mechanic mesh with some standard defects on it. This is the test result, and for a crack with 0.2 millimeter wide and 5 millimeter longs, the resonant frequency shift is 317 megahertz, and for holes The smallest detect diameter is 0.5 millimeter. So we also integrate the CSR with a feedback type oscillator. You can design the feedback loop to satisfy this oscillation condition, and then you can achieve self-sustained management, which means you don't need any external instrument. The sensor will generate a microwave signal by itself. You can see like this, and it can greatly reduce the hardware cost. So a big problem of the microwave sensor is that if there is any cracks, the EM energy of the sensor will leak through it. So because the magnetic mesh is used for EMI shielding, so it's totally unacceptable. So the biggest advantage of our sensor is that the oscillation will stop for cracks. So there is no risk of energy leakage. So this is the test results of cracks with different widths. You can see that our sensor can distinguish cracks with width of 0.4 millimeters. And we must notice that the microwave frequency we used have the wavelength about 40 millimeters, so it's a good result compared with its wavelength. So we can also perform oscillator steady state analysis, and we can derive the sensitivity of the output power and the sheet resistance. The output power of the oscillator decline with higher sheet resistance, and you can see the trend clearly on the right. It's a experimental result. So finally, we come to the summary. First, we introduce two typical defeats on magnetic mesh. One is cracks, and one is the high sheet resistance. And then we find that the microwave resonator can easily distinguish those two defeats. And finally, we propose a oscillator-based sensor which can achieve self-sustained management, and it can achieve self-switching effect. So this is all my presentation. Thank you for your listening. If you have some question, you can text a message or you can ask me directly. Thank you.